Okay, so welcome back to this complex analysis seminar online, and it's a great pleasure to introduce Lukasz Kosinski from Jagiellonian University of Krakow, who's going to talk about norm-preserving extensions of holomorphic function.
Okay, so I would like to thank you, Filippo, for invitation, and my talk is based on joint works with John McCarthy. He's from St. Louis, Jim Agler, and Włodzimierz Dzwonek, who is here. And let me start with some notation. So within the lecture, D will be the unit disk. H infinity is a standard space of bounded holomorphic functions on a set omega. And some part of the talk will take place in Hilbert spaces. So B of H stands for bounded operators on a Hilbert space H. And by ball of B of H, I will just denote the closed unit ball. So particularly if when dimension of H is equal to 1, then this ball is just the closed unit disk. And let me start with some with stating the interpolation theorem. And given endpoints z1 and zn in omega, and points, we call them nodes, and points lambda 1, lambda n. To interpolate means to determine this constant infimum of norm of phi, where subnorm of phi, where phi is a bounded function on omega that interpolates, that sends points zj to lambda j. And even more important is to describe all the minimal norm solutions. So if we denote this constant by t and divide lambda j by t, then our map will then omega, then h divided by t will map omega to the closed unit disk. Therefore, the dual statement is to determine if there exists a function, a holomorphic function on omega that interpolates. Okay, and optimal solution, and we are interested in optimal solutions. This is standard. This is quite standard when this is simple if omega is the disk. Then optimal solutions are just Blaschke maps.
Sorry, Lukasz, there is something I don't understand. So lambda 1, lambda n are
points in C.
Okay, so when you want to do this dual problem, you have to divide also lambda 1, lambda n by...
Yeah, I divide all of them by t. Exactly.
Okay.
And this is the same. This is the dual. Yeah. Okay. So if omega is the unit disk, then this is quite standard how to deal with this P object. However, the simplest, not much is known when omega is more complicated. The simplest non-trivial case was solved. It was solved by Agler in 1988. He has never published his paper, but then it was investigated more deeply in a sequel of papers by Agler and McCarthy in 1990, in 2000, and 2005. And they solved. The solution is far from being concise. Okay, but this is a little bit beyond the scope of this lecture. So let me explain why I started with interpolation. This talk is devoted to extension problem, and in fact, the extension and interpolation is the same. So interpolation problem, you have a set V, which is contained in a bigger subset omega. Usually V is finite, or at least discrete, and we are looking for a function that interpolates here. We are looking for the function phi. Okay. Extension. When we deal with extension issue, then V usually is a Vater set. V is a Vater set. Okay, so V has some structure, and we have a map F here that keeps this structure. and we want to extend it to the whole omega. So, which means that which means that we are looking for phi. Here, this phi will be analytic that interpolates. Okay, some analysis shows that what I mean by structure. We want to deal with some algebra that contains polynomials. Of course, the smallest one is algebra of polynomials. The biggest one is algebra of bounded holomorphic functions on omega or on V. So considering this, we can always pass to envelope of holomorphy of V, and then it is quite simple to show that this set is analytic. Therefore, as stated here, extension and interpolation is almost, it's the same. It's just another perspective. Okay. More motivation to study this extension. This extension is provided by theory of spectral sets, but I'm not going to go into this topic. So let me state what does it mean to extend F. So the problem is, so we have a bounded holomorphic function on V. Actually, this can be done for any algebra, as said before, but I will focus just on, for simplicity of the talk, I will focus on algebra of bounded holomorphic functions. And the question is the following. We have a bounded holomorphic function on V, and we ask if we can extend this function to the whole omega, such that the norm here is preserved. The same question actually can be asked, like interpolation, can be asked what happens for functions that are holomorphic on omega and are with values in B of H. But to this stuff, I will devote the last part of my talk. Okay, so this is the problem that we are going to deal with, and this is okay. And there are many extensions theorem, like teacher extension theorem. There is a Cartan extension theorem which says that you have a if you have actually Cartan, it's named Cartan, but it was given by Oka. If you have a function that is analytic on omega, then it can be extended to the whole omega. There is a Han-Banach theorem. There is a Ozaba-Takegoshi theorem that also shows if you have a function that is in L2, then extension is L2 as well. However, there are always extensions theorem. So these theorems that I've just mentioned are always extension theorem. Here we are on opposite side. We are not asking. We are not going to say that any function can be extended. Here we ask about V. There are many theorems like this, like Navanlina theorem or others. Okay, so this is on opposite side. So let me precisely state all necessary definitions. So omega is a pseudo-convex domain. V is analytic set. V here is an analytic set, and we shall say that omega V is NP par if any function on V with values in D extend to a holomorphic function on omega with values in D. So this is the same as here, yes? You can also scale this. So this is the same. We shall say that omega V is a complete non-preserving NP pair, if and only if for any, okay, here we can think also about finite dimensional interspaces. Then these are just matrices. If you're not familiar with this, okay, we can think about this in this way. And any holomorphic function on V with values in B of H can be extended to a holomorphic function on the whole omega, such that subnorm of F on V is equal to subnorm of capital F on omega. And if I have a time, I will discuss also what if there's isometric mapping operator linear. If this is additional linear, then we shall call omega V a complete linear NP power. Okay, and let me also tell you what is known. So the first known result in this direction was shown by Rudin in '68, who showed that If V is in fact a polydisc and omega V is a linear NP pair, then V must be okay. So this means that there exists a holomorphic R on omega with values on V such that R on V is identity. Okay. So, but this holds only under very artificial assumption that V is an embedded polydisc. The next result was obtained by Agler and McCarthy in 2003. They studied non-trivial case when omega is the bidisk under some additional assumption of polynomial convexity. So this means that actually the closure of V is polynomially convex. I will show you in the sequel where this condition comes up. And they showed that this is a NP pair if and only if either V is a point. So this is a bidisk. Either it's a point or it is a geodesic, or V is the whole bidisk. Okay, and a good question is, note that if note that if V is react, then this also gives us an extension, a linear extension operator of norm equal to 1. And the good question is if it is always the case. And it was shown 1 or 2 years ago by Agler, Wykova, and Young in 2012. I think that Dzwonek discussed this a month ago. They showed that the answer is no, namely they considered here the symmetrized bidisk. Let me write what this equal what this domain looks like. This is Z plus W. So here we have some, here we have some, here product, where both of them are less than 1. So this is a subdomain of C2. This domain is not convex, but it is C-convex, and Lampert's theory works here. And what they showed is that this set, for sure it's not smooth. Okay, so they showed that this set has extension property in the symmetrized bidisk. Okay, and the talk is divided actually into 2 parts. The first one is deals with the following question: given a pseudo-convex domain omega, we want to find all V, all analytic sets V, such that this pair omega and V forms an NP pair. And the second question is opposite to this, namely, given V, we want to find all G such that GB is NP pair. And the question is, can we concretely construct G? Okay, and okay, and okay. Now I will focus on this question. So I will show how to use Lampert's theory for convex sets. Let me introduce the following invariant function. This is called the Carrier-Todori function. This is CA of ZW is supremum of P of F of Z, F of W, where F is a holomorphic function on A with values on D. Here, P is the hyperbolic distance. So this is the hyperbolic or the Poincare distance on the disk. So in some sense, this is the smallest possible distance on, if D is convex, then this is the smallest possible distance. This is the Lampert's theorem. And Lampert's theorem says that all of them are equal if D is convex. And we shall say that an analytic set here is a C set if this invariant function on a small domain can be extended to is equal if CB of ZW is equal to C omega of ZW for all Z and W lying in V. Note here that this equality is always the case. Okay, and the first, okay, if you see there's a mistake here. Note that if this notion here, notion of C sets, is much weaker than the notion of NP pairs, because if omega V is NP pair, then V is a C set in omega. So this is because, as I said, C omega is always less than CV. On the other hand, if omega V is an NP pair, then this family, then any function here can be extended to the function on the whole omega. So actually we take the supremum over the same family. Then these two functions are equal. Okay. So let me show how to exploit this notion and how Lampert's theory can work here. And this is an example of a result, and I will show you an outline of I will outline how to show it to show how these methods can be used here. Okay, so assume that omega is triangly convex and V is in omega is algebraic. Then V is if V is a C set, then V is totally geodesic. Totally geodesic here means that it is totally geodesic with respect to Kobayashi distance, which means that if you have 2 points in V, okay, so this means that if you have 2 points in V and phi is a Kobayashi distance, Kobayashi geodesic, passing through Z and W, then the whole geodesic lies in V. Okay, so if you know that if this geodesic is in V, then if you find this geodesic, then the whole geodesic must be in V. Okay, so if this is set omega, this is V, then phi must be in V as well. Here we are in strongly convex case or linearly convex, so geodesics are unique. So there's only one such phi. Okay. So let me show you how to prove this. Okay, so the idea. So here we have a domain omega here, and V is in here. So this is V, and we take 2 points, Z and W. Okay, so let F is on V, such that for which this maximum here is attained, this supremum here is attained. So this is equal to C V of ZW. Okay, now, okay, so V maps V to D. So here we have a disk here. And the idea is that this set, the V of V must be big in D, in the unit disk. This is because if it were not the case, I mean that if V of V would be a smaller part of this, then we would be able to find a conformal mapping that sends this domain to D, and for which this distance between these 2 points is bigger. So distance between these 2 points is bigger than the distance between these points, the Polynomial distance. Now, if we compose these mappings, we get a map on V for which the distance here is higher. On the other hand, we know that these functions are equal on CT. So this gives a contradiction. So it cannot be the case. So this means that the closure of f of b is equal to the closure of is equal to the closed bidisk. Okay. So okay. On the other hand, we know that omega is triangly convex. So triangly convex. If omega is smooth, if it is C-smooth, then Lampert's theory works and shows that there exists phi f Okay, and if phi is a geodesic passing through this point, then there exists f such that which attains 1 exactly on phi of t, on the image of circle by phi. If omega is just smooth, then we need to use then Wong's theorem. Then we know that f is equal to 1 on phi star of t. Okay, so look, so this means that hello, yes. Okay, so this means that the whole but this condition means that t is contained in f of v. So this means that this set phi of t needs to be contained in the closure of v. And now polynomial convexity or algebraicity comes up, because if v is polynomially convex, then this means that the whole geodesic lies in v. So here the polynomial convexity plays an important role. Okay, so this shows that, okay, and the same idea works if sets are linearly convex. Okay. So in particular, if if omega is triangly convex in C2 and V is algebraic, and and omega V is an NP pair, then V must be either a single point or a geodesic, or it is the whole domain. Why is it so? This is a simple consequence of this theorem. This is because look, so we have a set V. We have 2 points, and we find a geodesic that passes through them, and it follows that this geodesic needs to be in V. Now, if there's any other, okay, so we know that this geodesic is in V. If we were able to find other point that is here, then we would then we could apply this idea to other points, and to show and we would show that there is an open set that is contained in V, and this automatically implies that V would be equal to the whole domain. So here dimension, it's important that we are in dimension 2. We don't know what happens we don't know how to deal with this idea in higher dimensional case. So we don't know what happens in Cn when n is bigger than 2. At least the case of the ball is simple to deal with, because we know we have exact formulas for geodesics. So then the answer, so the solution is that Bn V is an NP pair if and only if V is just an affine subspace of the Euclidean ball. Okay, and note that the same idea can work for the bidisk, but only for these points. If we have this point and this point and this point, okay, then we can apply the same idea to this function. Okay, but then still we can use some analytic geometry, and we can show that, okay, so by Stein theorem, we can embed V in this polydisc. Then we can project this, and we can use some analytic tools, and we can come up with this theorem that any C set of the bidisk is are exactly that a set that a subset V of the bidisk is a C set if and only if it is a geodesic or the whole bidisk or a single point. Okay, so these two notions are the same. These two notions are the same for the bidisk. And the advantage of this idea is that it can be generalized to a higher dimensional case. Let me just show what can be done for D3. The same idea working in Dn as well, but then the statement is more complicated. And this is what we're able to show with Zvonek. If V is an algebraic subset of D3, that is a C set, then V is either so either geodesic or the bidisc after automorphism, or it has the following form: Z1, Z2, H3, Z1, Z2, and okay, or either V is smooth. So this is a function, and if and we can show that if this holds, that this can be done for any choice of coordinates. Okay, an example of such functions would be example of such a variety would be like this: Z1 plus Z2 plus Z3 equal to 0. Okay, so this means actually that V is smooth and is singly streeted in each direction. Yes. Okay, so note that if U_r is equal to the bidisc, then we automatically get that we what we want. And it is a good question if this condition can occur indeed, and it turns out it can be the case, as the following example. So we cannot go further with this. We cannot get rid of this. This is shown by the following example of the surface. So here we assume that alpha 1 plus alpha 2 is bigger than alpha E3 for each choice of permutation, E1 to E3. Actually, Maciaszek showed recently that each M alpha is biholomorphic to M11. That was done by Maciaszek. And so M11 is just this. So M11 is just this surface. And it turns out that that M111 is a C set. Actually, M alpha is a totally geodesic sense. Okay, in the polydisc, geodesics are not unique. So here it's a totally geodesic in the sense that for into points in M alpha there exists a geodesic. There exists a geodesic that lies entirely in M alpha. We can show that we showed that M alpha is a C set, which means that invariant functions this characteristic function is equal on M alpha. Okay, this is obvious. Actually, it is not clear for us if this is an NP pair. We don't know this. So with this method of Lampert's sphere, we cannot go further to check whether whether M alpha has extension property in the polydisc. We need other tools. Nevertheless, M alpha appears. They come up also in interpolation as a family of uniqueness varieties for some interpolation problem on the polydisc. So they are quite interesting in its own, and that was also formally shown by Maciaszek. Okay, so I don't have much time, so now I will go to the second question. So as we see that, as we shall see, it turns out that V can be anything, even in convex domains. If omega is convex and V is analytic set such that omega V is NP power, then V can have singularities. Even if omega is convex, it can have cusps, and so on and so on. This is what we're going to show. So let me introduce two more definitions, because they will be quite convenient. By its short class, I just S of A, I denote the space of bounded of holomorphic functions of A with values in the closed unit disk, and S lambda 0 of A is the set of the space of this F that vanishes at point lambda. And in the same way, I defined S of A B of H. Here we consider functions on A with values in the closed ball, in the closed unit ball in B of H, and S of lambda is defined analogous in the same way. Okay, so first note that omega is an NP power if and only if any function that vanishes at this point can be extended to a function in a Schur class. This is simple because if we have a function on V, values on D, then we can compose this with a Möbius map. Then we can extend this map to F, composed with Möbius map again. Okay, so this is this is standard. So it's enough to extend functions within this class. This is what I mentioned. This is Cartan's theorem. This is a continuous linear surjection, as shown by Oka. So here is an analytic set. Omega is pseudo-convex. Both spaces are Riesched, so we can apply Michael selection theorem here. Michael selection theorem says that if we have a continuous surjection between such spaces, it is okay. So both. Okay, so this is what it says, and we know that it is continuous and linear. Then we can find a continuous selection, which means that there exists L on Y with values on X such that S of L of Y is equal to Y for each Y. And here L is continuous. So this is classical Michael selection theorem, and it can be used here. So if you use it we can find a continuous linear operator S such that L of S of F is equal to F for any holomorphic function on V. And for each F, we consider this set omega F and define omega as interior of intersection of this set. It can be shown, it's not so difficult, that V is contained in G. So this in particular would mean that it's not empty. By definition, it is open, and any such set is also pseudo-convex. So if we gather up these things together, we obtain the following theorem. If V is analytic set in a pseudo-convex domain, then there exists a pseudo-convex domain G. G here is contained in D, such that GV is an NP power. Which means that for any V we can find such G. Okay, let me show you two examples. So the first basic example is when V is the intersection. Okay, so V will be in C2, and V is intersection of two disks. So we have two disks. Maybe I will just to make things simple. I will focus on the case when V is the union of two disks. When V is equal to D times 0. Because I see that I have just 20 minutes. I don't have much time. So let me focus on this set. Okay. So V is the union of two disks. Okay. So G is a pseudo-convex domain. Then GT is an NP power if and only if T is a closed subset, is a naturally closed subset of G, and there exists a pseudo-convex set U in C2, and this function tau C tau, such that G is equal to this intersection. This actually it looks a bit artificial, but this means that GT is an NP power if and only if we can extend this function. So it will be this, sorry, this function. We can extend this function. Lambda 0 goes to tau 1 lambda. So this is a holomorphic function on V, where here tau 1 and tau 2 are unimodular constant, lies in T. This is the boundary of the disk. Okay, so the absolute values are equal to 1. So we can extend, so this is an NP power if and only if we can extend this family of functions. Okay, let me show you how, okay. Actually, even much more can be said. Let me come back to this for a moment. To this for a moment. Look, so this idea here works. This idea works also for functions on V in the ball of B of H, but only when H is finitely dimensional. This is because at some point we are using Montel's theorem, which fails which fails in infinite dimensional Hilbert spaces. Okay. So nevertheless, so actually we don't know how to show this for infinite dimensional Hilbert spaces. Nevertheless, in this case, this GV has NP property if and only if it is a complete NP, if and only if it is a complete NP pair. Okay. Okay, let me show you, because this is quite interesting in its own, how to show this. And here we need to pass to Hilbert spaces. This is something that this is a quite powerful method. That method was, for example, used by Agler in 1990. He has a paper in Invenciones where he proved Lampert's theorem using this method. This method was also used by Agler and McCarthy when they solved this interpolation problem on the bidisk. So it has many. It's quite powerful. It has many applications. And how powerful I will show you in a few minutes. So, okay, for functions in the Schuch class of the disk, it says that okay, so it says something like this: F is in a Schuch class on the unit disk if and only if there exists a Hilbert space and there exists a contraction U. So here it should be written like that. Here we have C, here we have K. So A is from C to C, D is from K to K, B from C to K, if and only such that F is of this form. And usually here dimension of K is equal to infinity. Dimension is finite if and only if phi is a Blaschke map. So if we want to use it, we need to pass to infinite dimensional Hilbert space. And the advantage of this is that the same works for functions with values in the ball in B of H, with the only difference that A here acts on a Hilbert space H, the same as here. Okay, and look, so we have a contraction here, and by Nagi's dilation, we can always find another Hilbert space K, such that this matrix here is unitary. Once we have unitary, we have a lot of tools that can be used. It can be used in here. Okay, so let me show you quickly how how to use this stuff. Okay, so I will need to open this. Okay. So look, we have a file. So suppose that we can extend. Suppose that we can extend this function. That this function here can be extended. Can be extended for any tau 1 equal to tau 2 equal to 1. Okay, then, okay. So now I take any function holomorphic on T with values in the ball of B of H. Okay, even in infinite dimensional case, B of H is transitive. Okay, but we can think about this as the closed disk. It's the same. Okay, so we can assume that phi of 0 is equal to 0. Then I apply this formula for this function. So this is a well-defined function. This function goes from D to the ball of B of H. Okay, maybe I will debar here. Okay, it's the closed disk. For the ball, it's exactly the same. Okay, and phi2. Okay, so this is phi 1. So this is phi, and this is phi of 0 lambda. It also goes from D to D. So we can use this model theorem, and we show that there exist unitary there exist contractions A, B, C, D. I will okay, this will be A1, AB, B1, C1, D1. This acts on C K1. This goes to C K1. So this is a contraction for this map, and there exists A2, B2, C2, D2. It goes from this to this, such that this one is not needed here. This is equal to A lambda plus B lambda plus, times E minus D lambda minus 1 C lambda A1, and this is equal to A2 lambda plus B2 . Okay, now, okay, so this is U1, and this is U2. Now we can replace U1 with, instead of U1, we can take this. This is identity on K2. So this goes from C plus K1 plus K2 into itself. And instead of U2, we can take this. Okay, so this also goes from K1, C plus K1 plus K2 into itself. Okay, so this means that we can assume that K1 and K2 are equal. Okay, with this. Now we use Nagi's theorem, and we find another Hilbert space such that we can find a Hilbert space M, such that this matrix here is unitary. Okay, and now we consider this mapping. I need to check how much time do I have. 10 minutes. Consider this mapping. So here V1 and V2 are unitary. Okay, so this mapping goes from T to the ball of B of M. Actually, it's not B of M, it's B of K plus M. Okay, and look, claim, if we can extend this mapping denoted by star, if we can extend star to a mapping defined on the whole G, then we are done. Then we can extend F. Then we can extend. Then we can extend. Then we can extend phi. Why does it? Why is it so? Because why claim implies the assertion. This is because if we extend this, denote this extension by phi. Then we can write phi in this form. So here we have some psi star star star. Psi is counterreaction, so this is less than 1. And psi is of this form, psi 1, psi 2, psi 3, psi 4. So a good extension is psi 1 plus psi 2 times identity minus psi 4 minus 1, psi 3. This is a good extension. A good extension of phi. Okay. I don't have enough time to show you the claim, but the idea for this is the following. So we can assume that V1 is identity, and then by the spectral theorem, okay, so this is for finite dimensional case. For finite dimensional case, we can assume that V1 is identity, and then V2 by spectral theorem is equal to U. Here we have some diagonal operator. We have U minus 1 here. Okay, so this means that we need to extend this map. Okay, so because this function can be written in this way. This is U times lambda U minus 1. This is lambda, and this is U d1 lambda dk lambda U minus 1. So the only thing we need is to extend these mappings here. Here, absolute value of dj is equal to 1. Okay, so this is for finite dimensional case, which is never the case actually here, because here m and k needs to be infinite dimensional. But in general case, we need to use some spectral theorem and such tools. But at least I think that it's seen that this is doable. So let me come back to the slides. Okay. And the same can be done actually for the symmetrized bidisc. So this covers the case of two intersections of two discs intersecting at one point. And okay. Look at this set. So this is an analytic set in CPE. This set has a cap. Anyway, we can still use we can use the dilation idea or Agler's methods to this set. We showed that this is a 2-branch cover. Then we need to develop the theory of even sure functions on the bidisc, and it says something like this, that okay, there's a model for these domains. For this, namely, we can show that a function is an even function is in the class of even short functions on the bidisc, if and only if there exists a decomposed Hilbert space M and unitary U, and the block matrix such that we have this formula. Okay, I'm not going into details here. I will skip this. Nevertheless, the following is okay. So here is ZU. So here U is M is decomposed Hilbert space plus M2. U is A, B, C, D. This is unitary. And this here we have space M1. And here is space M2, M1, M2. So we can define, it should be less than 1 here, sorry. We can define G in the following way. Point G is a set of points such that this norm, okay, and ZU is just AZ1, B, Z3, C, Z3, Z2, DZ2. Okay. So Z is in G if and only if this norm of ZU is less than 1 for any M and any U. Note that it follows immediately that G is convex. Okay, G is a convex set. And actually we can compute this explicitly. G is the set of points in the polydisk that satisfies this equality. I don't see how to do convexity from this formula actually. That's why I mentioned that G is convex. And we can show that G is convex and G, V, so V here is this set, is NP pair. So as we see, cusp are also allowed. So V can be anything. There is also, I have a few minutes left. What's not known for us is whether what happens if we consider functions with values in the ball of B of H, where when H is infinite dimensional. As I said, this is because of the lack of Montel's theorem there. Nevertheless, there is a weaker notion, which is which I mentioned. This is linear extension, and if we know that there is a set, if we know that if this power is a linear NP power, then it is a complete NP power. This is because how we compute norms of operators. This is a combination of linear maps. But surprise, it was a bit. It was a surprise for us that the symmetrized bidisk is not a linear NP pair, which means that because we have NP pairs, we have complete NP pairs, and we have linear NP pairs. And this notion implies this one, and this one implies this one. Nevertheless, we thought that these two notions should be connected. But okay. But let me finish my talk with saying about this condition for the polydisk. In the polydisk, actually, this condition is quite simple to deal with, because if this is a linear NP pair, then V must be a lower dimensional polydisk. And this also works for any convex domain. So this linear extension property considered by Rudin is quite simple to deal with. And the argument for this is the following. Argument for this is quite simple. Consider this extension. Zj can be extended to Vj, where Zj are coordinates maps on the polydisk. These are coordinates maps. And in this, so phi is phi1, phi n. And it is quite immediate to see that V is contained in a fixed point, in the set of fixed points of phi. It's quite standard. Actually, it was shown by Viguet. It was Viguet who showed that this set is, which means that it's a smaller dimensional polydisk here. So we see that having this tool in hands, we can easily obtain this result. And I think it's time to stop my talk. I wanted to mention a few questions, but maybe I will skip this, okay? And I will stop now, okay? So the talk was based on this.
Very nice talk, Lukasz. So are there questions? Please unmute yourself and ask your question if you have. Okay, no questions. So this is not really a question, it's more a philosophical something. So when you look for this C Caratodori set, no?
Yes.
So they are totally geodesic. Do you get also that they are totally geodesic in the sense that the real geodesic are contained inside, but then...
this is a good question. This is a good question. This is something that we don't know actually, but we want to study this.
Mm-hmm.
This is the case in the symmetrized bidisk. Okay, this okay, even in the two just disks, the union of two disks. Yes, this set there is. It's not geodesic for sure. It's not totally geodesic, but this is totally geodesic in the sense that was mentioned by you.
Mm-hmm.
Yeah, this is something that we wanted to study. Actually, I don't know what the answer is, but I think that the answer to this question might be interesting. I don't know what is it for this analytic set in G, the one that has a cusp, but yeah, but this is a good question, and I don't know what the answer is.
Thank you. Other questions, comments? Okay, so if not, we thank Lukasz again.
Thank you.